Hello everyone. I want to thank you the opportunity to be here explaining the idea behind the diffusion complexity mapping. That is a scalar metric that we developed for usage in clinical DTI protocols. So basically the background here is giving the idea that the diffusion weighted images is actually a way to collect signals from the movement of water inside the tissue. And then using this, you have the possibility to represent this dislocation, this water movement, using the diffusion tensor imaging. However, it's well known that DTI have some struggles, and the main ones is very common in study along the time is the crossing fiber problem, which is difficult to represent in some locations where you have more than one restriction or a conjunction of two or more fibers in the same voxel space. And then the tensorial representation does not give you a very precise way of the water movement inside it. And then that is the basic problem that you're trying to applicate some new ideas. So what it can do to give more emphasis or more focus on areas that is naturally lower signal for the classical DTI maps. Here is the idea to use the LMSC, the Lopez-Ruiz-Mancini-Calbe statistical complexity measure, to create a possibility to use the same data that we acquired before, but giving another calculation to give more focus on areas that is represent some structure that relies on the middle between the highly restricted structure, like white matter, for example, and a very free movement around. So the ideal gas here is representing actually the CSF environment. And in the middle, you can place some tissue that have some structural organization, but also gives relatively more free movement for the water. So basically the idea is that the gray matter relies in the middle of this range. Then a very quick way to represent our methodology here is acquiring the DWI sequence. It's basically the raw data using in DTI and collecting all the diffusion directions using the diffusion calculation, the basic diffusion calculation. And all those gradients can give us a diffusion probability distribution in which our brain tissues can be differentiated using our complexity measure like this one. And the voxel you can calculate it and create a map like this one in the left side. And basically the calculation for the complexity is using the information, the entropy information, and multiplies for the disequilibrium function. Well, to evaluate this, we used the open access OASIS and tracto-inferon dataset, which are both have excellent data to analyze it. And we simply calculate the signal intensity and contrast noise evaluation to understand how our mapping is behaving or is presenting the results to us. Okay, some examples here just show our results in comparison with FA and the ADC. And the first thing that came up to us is that gray matter actually shows the maximum intensity value for this DC map. Then it's good to see that our DC map presents a very nice separated regions in the image, so we can differentiate all the tissues. If you want to get our code to make some experiments or check it out our results, our methodology, you can take our ITK sample code using the basic framework from Insight Toolkit, which is a very good alternative for command line interface. And also you have a 3D slicer extension, which gives a graphical interface to help visualizing our results and our output directly on 3D slicer. And also our paper that explains more details about this technique. And thank you very much again to having this space to present our work.